All right, folks, thanks for waiting while people trickled in. We've got Ian Latter here to talk to us. Ian's a 20-year veteran of the IT industry who has spent the last 15 years working in security in a number of positions, including penetration tester, security architect, and most recently in a security governance role at a blue-chip corporation. Ian teaches practical threat intelligence course at Black Hat and has spoken at key international hacking and security conferences, including COSAC, RuxCon, and KiwiCon. If he had the spare time, Ian would be pursuing a number of private software and robotics projects, including the Barbie car that he promised his daughter. Wiser friends have advised that he finish this project before she's old enough to ask for a real Corvette instead. Please put your hands together for Ian Latter.
Thank you, and thanks to BSides. And today we're going to talk about through-glass transfer as a remote access exploitation tool. The key messages for this session, the messages that I want you to take away from this session, is that this is a current security architecture flaw. So if your current security architecture is flawed today. I published everything that you need to know about this already. It's all up on the website. From first principles to demonstration and full code release, proof of concepts, all included in the white paper. So this is for the first version of TGXF, TKXF, and TCXF, which you'll see in this deck. The impact will probably be significant. Today it will be much more significant. There are no constraints to data theft for remote workers or offshore partners. And there are no easy answers, though the paper has some suggestions. My career, I've been on both, as you heard, the red team and the blue team. I'm currently on the blue team. I have a number of hobbies. My daughter's Barbie car, unfortunately, is one of the many projects that have suffered because of my lack of time. And hopefully we'll get on that at the end of this year. I want to give credit to a number of researchers that have worked in this field. It seems that quite a few of the technologies involved have actually been invented uniquely multiple times, and I did the same thing again. You'll find some technologies in here that have been presented before. I didn't know that at the time when I wrote it. I've even written to some of these people and make sure that I've got their blessing. There's a lot more references on the website for people who've worked in similar disciplines and future useful disciplines for this. And I learned about one more yesterday that was presented in October in Budapest, I believe, that I've got to look at. So let's look at the problem space. Now, it's my assertion that any user-controlled bit is a communications channel. So my validation for this is that the screen transmits huge volumes of data. So I want you to imagine the screen as a bundle of fiber optics that have been cut clean through. So those fiber optics are pumping bits at you from your screen. So then can the screen be transformed into an uncontrolled binary transfer interface? So my technology solution, my proof of concept, my brain went back to terminal printing, VT220. At that stage, terminal printing all we did was redirect the virtual terminal to a file, to a printer or to a file. So data didn't actually leave the screen. Same as what we did with X, Y, and Z modem protocols. There was a VHS tape backup product that I got to see when I was working in an electronics store as a kid. Grayscale blocks were actually stored, they were played out of an AV port and recorded on a VHS tape. When you play back that tape, plug it into the video in on this board, it could actually restore data. So you could see data in blocks on video. It didn't technically come out of the screen, but it was close. The first one that I'm aware of was the Timex Datalink watch from 1994. It was a Microsoft project with Timex. It programmed the EEPROM through the face of the watch. The little window to the EEPROM was exposed to the screen, and I've got a demo of that for you. It was dependent on a CRT. There's a couple of projects that have been out since that do it with a TTL LED. Took about 20 seconds to transfer 70 phone numbers. And this is the ad. This was from the first computer watch revolution 20 years ago. As you can see, configure your diary. You remember this interface. And then to transfer it, we hold the watch up to the screen. And those lines actually emit patterns that the watch uses to store the data directly in the EEPROM. So that's data emitted from the screen. under some very specific circumstances. Now, I'm not going to go, given the audience, into the complete history of QR codes. Needless to say that I wanted highly distinguished, highly machine-readable, recognizable and 360-degree scanning, the native features of QR code. Once it was standardized, we also got inherent error correction and support for deformed images, for deformed codes. It's got large capacities, but I don't use that in this demonstration. So the Zen moment here is I want you to consider a QR code on the screen as a layer 3 packet, a datagram packet. And it's captured within the ether of that display device. So then at this point, we need to get from one QR code to another to create a packet flow. We simply replace one QR code with another on the transmit side. On the receive side, all we have to do is use video instead of a photo and not exit. But this creates a number of problems at layer 4. So it's a unidirectional interface. I've got no signaling back into the screen. I can only receive. This means no synchronization and no flow control as well. It means I've got to oversample the screen to make sure I've captured the packet. When I oversample the screen, I get duplicates. When I try and deduplicate it, I've got problems because that was possibly intended in the application layer. So I need some sort of transport protocol. If I use the smallest QR code, version 1, it's 14 bytes in size with 15% error correction. I take the first byte and turn that into a packet header. So now I can choose different flavors of packet. I've created a control and a data frame. In the control frame, in the data frame, the first bit toggles the packet type, and then I've got a counter and reserve data, and then the rest of it's payload. It's just source data modded to the packet size. Originally designed just to transfer data as a file, transfer one file at a time out of the screen. The control frame, very similar, control bits set to control, and a couple of message types, a major type and a minor type, and then the payload is the contents for that control message. So you can see the messages here, file name, file size, QR code version, frame rate. Most of these messages are actually irrelevant to the transfer protocol because the receiver can do nothing but work with what's been sent to it. Really, all of this is for user interaction, user interface, to show the user details about the progression of their transfer. At this point, I can do a one-way transfer between one or more receivers. Don't forget, I can have multiple people seeing the same screen. I've got features at between layers 4 and 7 for high latency interrupted transfers because I can only mod packet the distance into the file, kind of like BitTorrent. You're putting a bit at a time, a chunk at a time. It includes error detection both natively and end-to-end because I put a CRC in the stop message. It requires of layer 3. These are arbitrary. I've set these up in the protocol just for the proof of concept. 1, 2, 5, 8 or 10 frames per second. I'm assuming a commodity camera on the other side, so I probably can't go, like I'm looking for a third of the camera speed, so 30 frames per second. I want to max out at about 10 frames. QR codes, versions 1, 2, 8 or 15, just to give a spectrum. And then binary encoding with 15% error correction. Now the problem with the error correction that's in the QR code is if you get depending on the type of data, if you get close to the suggested capacity, it may spill over. And then in this protocol, that means suddenly you get a different size QR code in the middle of your stream, which can break recognition. I've arbitrarily selected a smaller reliable capacity, which won't cause that spillover in 15% error correction. So the smallest packet size I'm working to is 15 bytes per frame, and the largest is 408 in this example. To give a quick hello world file transfer, that's control start file name hello world. It's got to fit in the packet, smallest packet size. Start control file size, I'm sending you a 13-byte file. Start control, 148 bytes per frame that I can send. Start control FPS, I'm sending 5 frames per second. So you can now display a status bar and a time estimate. Data with a counter of 0, there's my hello world text. And then I send a control stop complete with a CRC32 so you can validate the complete file transfer. This is an example of what that looks like. This is a file encoded in a TGXF transfer graphically. So that's what you'll see on the screen. If we update those layer 3 configurations with frame rates, frames per second, the scale that we get with the smallest frame at 1 frame per second is 80 bits per second through to about 32K. It's arbitrarily set by me in the configuration of this protocol. Also note that this is only limited by the receiver. So if I had a high-speed camera, I could get closer to the frame rate of the screen. Here's an example of a letter that I sent off to the Office of the Australian Information Commissioner after February last year, when he changed the rules to say that use of a system was different from disclosure of data in that system. When offshore workers use data in my system, that data is considered to be onshore. When the data leaves that system, that data is considered to be offshore. This protocol makes that possible. You can see here, if you look very, very closely, that it's in flight mode, and there's a yellow status bar off the bottom there that's showing, oops, sorry, wrong spot, off there, that's showing the status of the file being transferred. This is an app that you can pull down now, and that was a real-time transfer of that PDF to the phone. So that's Google being used as Dropbox. Now, the reason why I kept the version 1 QR code and wrote the protocol around that is because natively it's 21 by 21 pixels. 21 by 21 pixels happens to be able to be rendered in a native 80 by 25 text window. This is an ANSI version of the same sequence, generating using simply space characters with white on black and black on white ANSI codes. So that sequence will come out from a terminal window. So, if the TGXF transmit software was on this laptop right now, I could exfiltrate data file by file through the screen. And the binaries for that were made public a year ago. But then how do I get TGXF onto the laptop in the first place? Well, if any user control bit is a communications channel and I have a keyboard, then I need a programmable keyboard. The Arduino Leonardo has native USB HID support. It shows up as a mouse, keyboard, and joystick, I believe. The DigiSpark on the top has 6K flash. It was a community project. The Leo stick that I can buy at my local electronics store for about 20 bucks is below at 32K of flash. If we put data on there, we can upload it. But what do we upload? Well, we could upload source code because it's text, so we can type in text. But that kind of sucks because secured systems won't have a compiler. So what we really want to do is upload a gzipped version of the binary. We gzip it, we hex dump it, so it's compressed. It's dumped out to a bunch of hexadecimal characters, so we're from 0 to 9A to F, so we can type it in. And then I simply wrap around that maybe some printfs for bash or print for Perl, so that whatever gets put in I can run and it'll give me the binary back out. This is the file uploader. Here's an example of a HP thin client that my wife bought off eBay for me. I don't know the administrative password for this device. When I plug in my file uploader, actually before I plug in my file uploader, I'm using PuTTY to SSH to another machine and open a text editor. When I plug in that Leonardo device, a whole heap of questions are going to come up asking to add drivers for the Arduino side of the device. I'll cancel those because I don't have the permission to do anything with it, but the USB HID keyboard will be accepted by this device out of the box. You can pre-program the HID on these devices, so this could look like a Ciccone HP keyboard, for example. So I've plugged it in. There it goes, typing in the data as a script. It'll get to the end. It's flashed to tell me that it's finished. It gave me a beep. I can quit, change the permissions on the file, run the file, outputting it to the gzip file, because remember it's the gzip binary that's encoded in there. I can gunzip it, change the permissions of the payload so I can run it, and then run the payload. So now I've got my binary on the target system. But wait, if there's now no barrier to getting something onto the target system, then technically I've got full duplex. I've got data coming out and data going in. So I could actually replace file transfers with full-blown through-the-screen networking. To do this, we need to make a few tweaks. First of all, the USB HID keyboard interface is a polled interface from the hardware. It's polled once every millisecond. The typical implementation sends a key packet followed by a null packet. That's not necessary, but I kept it that way because it was easier. It contains up to 6 keyboard keys by code. There's no native binary mode in here. It's automatically deduped, which is something I was not expecting, so I had to, we'll get to that in a sec, but data is removed irretrievably with dedupe. we have the same problems we had with TGXF. Data going into the system needs some sort of transport protocol. Although it's unidirectional, although the status LEDs could be used to extract data, and when I wrote this, I didn't know that someone had done that. There was a project that I'd read about, but I can't find code for, that shows 10 kilobit per second data exfiltration through caps, num, and scroll lock keys. Data is we want to create a binary payload by encoding it in hexadecimal, which halves the throughput, and retaining the key clear means we're getting about 3 bytes per packet per 2 milliseconds peak performance. There are a few things limiting that in the Arduino as well, which I think I removed most of, including, so I needed to correct for deduplication, and that takes about half the keyboard, I think, if I remember correctly. At this stage, there's not enough space in that packet to take a whole byte out for a header. So what I've done is I've bookended a sequence of keys and said this is a control and this is a data. And then I've taken out anything file-based. I really just want to stream. If I take that Leonardo device, which is my keyboard emulator, and I add a USB serial device, the attacker now has a USB serial port where he can send binary data, and that's encoded as keystrokes to create this keyboard stuffer. So now I can send binary data and have it typed in encoded for me. And I made a few extra changes to the Arduino native code to make that run faster. That's the TKXF side. On the TGXF side, I strip out anything that made it file-based. I really just want streams. So I've got streams in and streams out. This is what happens when we combine into a single architecture. On the left, at the personal computer end, the attacker end, I've got a listening TCP socket on my attacker device. What I send out of my serial port goes into the end user compute device, the enterprise device, as a USB keyboard. So it's now typing in, so all you see is a keyboard. That goes into the code at the other end that sends it out of the TCP socket. Coming in from the TCP socket on the enterprise side, data is encoded as packets on the screen. That's decoded, in this case, via a camera, and what's been decoded is sent out of the socket. So now I've got a TCP socket on my device, and I've got a TCP socket on the enterprise device, and technically they're air-gapped. The only connection here is a keyboard. The reference implementation has 12 kilobits per second up, maximum. I don't think I achieved that. In theory, that could go up to 32K. I've made some suggestions for doing that. I'm not going to pursue it. The reference implementation for TGXF at this point has 32K max down. At this stage, we've got bidirectional binary clear serial communications. It's a native network socket interface, so anything will run over this. And it's insanely portable and massively vulnerable. An example of this is that you can run PPPD over Netcat over that interface and actually get a native IP interface as well. And I'll show you a demo of that in a moment. In terms of architecture, what have we done to the enterprise? Well, firstly, what is TGXF, TKXF, and TCXF? These are storage-based covert channel attacks, although some have suggested they're overt channel attacks. Secondly, where is the enterprise in all this? I've been talking about this device, but where is the rest of the organization? Well, in the enterprise, we abstract the screen and keyboard on the organization side. So when I'm offshore, as an offshore worker, this is what enterprise looks like at layer 7. I'm out here. I'm way back out here, or from your perspective, out in the audience, offshore. As I connect into the organization, I go through my Citrix jump host, my VDI, maybe my SSH jump box, to the most sensitive box in the organization where I've got to work. The pixels rendered on the screen in that SSH session from the most sensitive part of my organization are passed clear through to my screen offshore, uninterrupted. So it doesn't matter how many gates we pass through, the screen is clearly passed out and the keyboard's clearly passed in. In terms of the model, on the bottom you'll see who owns what. The attacker's on the left and the enterprise owns everything to the right. I don't need to compromise the end user device that's been given to me offshore. There's no AV that's going to tell me that this has been compromised, because all you've seen is a keyboard plugged in and a screen in front of it. And I can make that keyboard head look like the keyboard that I unplugged. The client that's running on my end, on the attacker device, is outside of your visibility. The client that's been deployed internally hasn't been deployed on this device. It's been deployed deep in your data center where that asset is, where I have access to. Right back next to that little beer in the corner, where you don't have AV, where you don't have DLP, where you don't have malware detection. What's it look like? On the left, I've got an attacker device marked with red tags. Then I've got the EUC device, the HP thin client, and an application server marked with the yellowy green tags. You can see I've got the camera sitting in front of the screen, and I've got a keyboard stuffer plugged in. I'm running it up with the 2 PuTTY sessions from the EUC box from the thin client through to the application server. And so I'm running this session from the application server. That attacker box is not connected to a network. I've run up PPPD on the application server and on the laptop. And now I'm SSHing from the laptop, which has no network connection, to the application server, which is on the same IP network as the laptop. You can see it slowly ticking away, and I'm sorry about my bad elbow acting because it got in the way of the autofocus. It does clear up at the right spot. I'm accepting the SSH key on the left. We're going to wait as it ticks over. Now I've got to type in the password. And now I've got a shell. So now I'm sitting on that application server. The only thing you're seeing is the QR codes on the screen at best. That's a running PuTTY window, and the encoded key codes that are typed hex, effectively. I'm now doing an LS, and you can see that slowly ticking over. So that's TCP, that's SSH on IP, PPP over TCP over screen and keyboard with one part of that over SSH. Technology solution 2. People get really hung up on the QR codes. Yes, I can go pay my DLP provider to go and filter QR codes. Yes, I know that. In the original paper, I said that was the obvious next step. It won't work. At Christmas, I did a version that ran on pure ASCII. So the datagram at layer 3 can be anything. It can be pixels, it can be Fortune 500 logos. I'd love to see people filter off Fortune 500 logos. It could be letters, words, or phrases. I've chosen some ASCII zeros and ones. In this case, the letters using text letters means I can also make it clientless, so I don't need to drop a binary. I can now do it in bash. And it's still minimal server-side indicators of compromise because I've just got this 300-byte bash script, and it demos the futility of tracking QR codes. That's the bash code. I've put it a specific font and color because I'm using OCR in my proof of concept. It could have been done better, but it was done quickly. I'm now getting rid of the camera. I'm going to use an AVA media gain capture device. This plugs into the HDMI port. These devices are designed to allow you to upload your game videos from your Xbox and PlayStation to YouTube. In this case, I'm capturing it down to that little orange USB key as an MP4 file. This is a 1 kilobit per second upload that we're going to capture and then retrieve from a box by looking at the MP4 video. Now, last year at one of the bars, I was asked about the red room in this scenario. The red room is that special room in your organization where the secret sauce is kept. Now, in our offshore case, typically we regard the offshore environment from tier 1 organization perspective to be a lockdown room where things aren't allowed to go in and out. I'm yet to see one of those rooms pass a physical security audit, but let's roll with it anyway. The red room argument was put to me. The rules are a device can enter the red room, but it's got to be blanked except for the firmware. It shouldn't have a problem, so we can get the device into the room, but the device, when it leaves, also has to be blanked except for the firmware, so how do I get my video file back out? The argument I put back was Captain Coon says, be creative. If you don't know the movie reference, you'll have to look it up. This is the bash program running with a capture. I've redirected etc password to file descriptor 3, which is what I'm going to read in encode. You'll see we still have the same format. The data packets have a counter on the left and 1 byte per packet on the right. It's a really tiny TGXF. In the next video, I take that capture and I play it back. So I've taken this MP4 file back to the attacker's computer. This code is now reading it frame by frame and displaying it on the right. You'll see if you're close enough, you'll see little boxes flashing around the text. That's the OCR going nuts and showing where we've actually found characters. As it runs, you'll see it decode on the screen on the left. So line by line, you'll see etc password come out, which is what that is over there. So there's no limitation simply because I've got a text window and you've taken QR codes off me. If you've got more time, you can have a look on YouTube. That video ends with the correct I don't know if I did an MD5 on that one, but the others all end with the correct MD5. Solution 3, this year I'm making good on the pixel threat. People say, yeah, but QR codes and text, it's all very slow. I don't really care. You can't steal enough. Fine. TGXF has been updated. I now do a CRC 32 per frame because I'm doing massive frame sizes. The datagram protocol is HTML5. We're using HTML5 canvas and JavaScript. So at this stage, what I'm uploading is a whole bunch of HTML code, about 30K's worth. Even though I said 20K there, it got a bit bigger. It's still technically clientless in that sense. It feels a bit clienty to me, but people still seem to think that it's clientless. Again, the indicator of compromise is quite lightweight here. You're really just looking at that script and a HDMI plug, a script in the data center, HDMI plug. This one is graphical, which means you'll be doing it from your XenApp browser or from your VDI desktop, for example. So you're still in the environment exporting offshore. Again, demos the futility of targeting a specific implementation, because if there's one message you take away from this, is that I can change this infinitely. Same box, the AVA media gives me 1.3 megabits per second at 2 frames per second with 1 bit per pixel. So black or white, it's either on or it's off. I'm doing 1280 by 720 by 60 frames per second capture. This box doesn't run anywhere near that fast, and you'll see that in a sec. 100 kilobytes per frame now is being captured, and again, we take this offline to do the MP4 read. I can store this on my 25K Arduino, plug it in. There goes my code. I'm typing it in. So all I had to do was open a text editor on the desktop at the other end. This is a web browser window, F11. This is Firefox, but it also runs in Chrome, so it's in full screen mode. What you'll see, I've selected the 5.5 megabyte white paper that I originally wrote on this. The big red frame was a syncing frame, and then each of these is obviously the data encoded bit by bit, 1 bit per pixel, black or white, being captured by a screen, the HDMI capture tool. When it completes, you'll see up in the top corner, up over there, the speed. Yeah, and there you go, 1.3 megabits per second. So we take that MP4 and we decode it. I've got debug turned on. Every single frame line in the text window is another frame of video that's going past. What you'll see in this video, because the AVA media struggles to keep up, about 50% of the way through the file transfer, you'll see this sort of pixelation as the screen tries to res up. It's almost like it ran fast for a while and then slowed down because it's designed to ultimately upload videos to YouTube, so they don't need to be high quality. When it does that about halfway through the video, you'll note a whole heap of errors pile up between recognized frames. So it's getting control codes at the moment. They're tiny up here. You'll eventually see a burst of data here. So that's all those control headers. Then this is a little burst of failure, so didn't quite get the right data before we finally got a valid CRC on a packet and stored 1 packet. You can see the gap of the number of frames that are all duplicates and perfectly readable. So we dump them all because we don't need them. What will happen is those one-off little errors will suddenly stack up when we get halfway through the video. So there's still just a couple of errors, still just a couple of errors. Somewhere here, you'll see that the video does some weird resing thing where a whole lot of data slowly gets populated and it takes many, many frames before I get a perfectly clean frame. We're starting to get more errors, starting to get loads of errors. We almost run out into the next frame before I get my perfect frame. That's because of this device. In the bottom corner over here, you can see the PDF that's slowly being drawn out of this video. And when we get to the end of the transfer, which is coming up, you'll see that the CRC validates for the file. So we're almost there. Couple more frames, loads of errors there, but we still get enough. We still get a couple of good frames, so we've got enough. And that's it. The CRC validates. I now have a PDF. When I double click on it, you see I've got that entire file back. And that was a 1.3 megabit per second upload. So, it's not good enough for a conference. For another $30, you can have a professional card. This is a Blackmagic designed Decklink mini recorder. I didn't read the description properly. It's a YUV card, not an RGB card. I have no idea what the AVA media was. I never went back to the manual. The problem here is you don't get raw RGB data. If I had raw RGB data, there's no reason that I couldn't take every single frame perfectly every time. So we'd be talking full-size picture, 60 frames per second, depending on what's possible offshore, give or take the bandwidth and the setup of your environment, right? Same resolution, same number of bytes per frame, but I'm now doing 8 frames per second at 1 bit per pixel, which gets me up to 4.7 megabits per second. For the low price of 10 times as much, I'm now at $1,500. That Blackmagic designed Decklink 4K Extreme 12G card is designed to capture 4K video at full frame rate. The only reason why I'm not showing you a gigabit download today is because I couldn't parse the bloody video file in Linux. What I got, FFmpeg came the closest, and it allowed me to get 3 bits per pixel, which is giving me 12.1 megabits per second. But that's the only thing stopping me from making this faster. I didn't have a Windows box to try it on. So 12.1 megabits per second, I'm doing 10 frames per second at 3 bits per pixel. We're now talking 300K per packet. Big packet sizes. I shouldn't be using CRC32, but it works. This is what it looks like. There's the sync frame, and that's the 5.5 meg file being uploaded. This is what it looks like to decode. It's so quick I can't even size the screen fast enough. It's already got the control packets. You notice it's almost perfectly clean. There's only 2 CRC errors in the entire transfer, and it's not enough to upset it because it gets the right frame. That's a CRC validated transfer. Back to the enterprise architecture. If we take PPP back out of the example, because that's cheating, that was the only place where we required super user access. To create an interface requires permission. If I take that out, every other thing I've shown you, it has no privilege escalation. Those protocols can only do what the user can do, what I could do. So with the permissions I had, it can only type and read what I could type and read. The distinct properties of what's changed here seem to revolve around volume, accuracy, structure, and utility, and the paper goes into some thoughts about what you could do around that. The legal problem, the reason why I started all this is back in February 2014, the rules changed so that they relied on use versus disclosure in Australia. They made the organisation that's doing the offshoring, the Australian entity that brought in the offshore agency, legally responsible and liable for what happens when that data gets disclosed. So I'm allowed to bring people in to use it in my systems where it's controlled and within Australia, but when that data is disclosed and it goes offshore, if it's used for a purpose other than it was collected, then it becomes the Australian entity's liability. And there's some similar rulings in HIPAA and FISMA. There's some interesting rules in there too. They all rely on the difference between use and disclosure. This also includes, in this particular set of rules, unauthorized access, where the user discloses it themselves, so the offshore user actually hacks it, like what we're doing here, if you didn't take reasonable steps. Of all the reasonable steps listed, the only one that makes any sense to me is monitoring. So the question is, what is reasonable monitoring? Butler Lamson in 1973, this is the world's oldest zero-day, was looking to restrain data being transferred between people of different classifications. His conclusion was probably cheaper to accept the risk and try and bound the capacity than trying to bound the capacity of all covert channels. His material became part of TCSec, so the DoD specification. So B2 and B3 trusted systems said that a high covert channel bandwidth was probably 100 bits per second, because 100 bits per second was considered a useful terminal. So if a terminal is leaking at the rate of a useful terminal, it's probably not a secure terminal. From this presentation today, I have not shown you a demo that ran under 100 bits per second, including the text demos. HDMI, as I've already mentioned, at 1920 by 1080 by 24 bits per pixel by 24 frames per second, which is low for that spec, will run it faster than gigabit per second. So far as acceptability in the DoD spec, they've capped it at 1 bit per second for a covert channel. But you have to be able to audit any channel that can exceed a rate of 1 bit in 10 seconds. Is your organization today able to audit every keystroke, every pixel, every change in caps lock light that can happen at 1 in 10 seconds across the entire organization, because that's what these people are suggesting is reasonable. I'll give you a commercial example, and we're about to wrap up the talk. I put this risk calculator on the website a month ago, so you can play with it in your own environment. In April, the FCC went after AT&T, from what I remember reading, for losing 280,000 records through their offshore centers in, I think it was Mexico, Colombia, and the Philippines. That was a $25 million settlement for 280,000 records. That works out to about $89 a record. That's quite low compared to the Ponymon figures of $188, $189 per record, but this is just the fine. This is just that suit. If my offshore workers were limited today to just what this calculator goes as low as memory. So I might be able to remember a word a day, for example. There's nothing stopping someone from remembering a word and taking it home. But I'll start with something a little bit more meaty. Let's say an A4 page. 1,000 words is about 5 kilobytes. I've set a record's 2 kilobytes. We're going to treat it as a complete binary object. You can probably go harder. We got one attacker. So one attacker, 4 days' time, taking an A4 page home per day of record data. We're talking at the rates from the example we've looked at, 10 records in 4 business days, or $1,000 bucks. Let's say they do 10 times that. Let's say they take 10 pages home. We're still less than 10 grand, and we're still only talking, maybe 100 people. As long as the FCC doesn't give bulk discounts, what I've shown you today would be capable of changing that figure to somewhere in the order of 87 million records in 4 business days. That's 8-hour days. That's $8 billion worth of cost. But I don't have to work in 8-hour days anymore. I can set this up at 9 a.m. today, and I can pick it up at 5 p.m. tomorrow. So that can happen in 32 hours. In a 24-hour day, I can take 65 million records worth about $6 billion using that case study every 24 hours. So I can take all of the United States, every man, woman, and child in 1 week, or everyone in Australia in 8 hours, because we're a little country. So the message to take away here, the new equilibrium, use versus disclosure, they're functionally identical. There is no difference. If I can see it, I can have it. You've uploaded it to the room. Offshoring, right sourcing, best shoring, whatever term you currently want to use to describe remote access for untrusted or semi-trusted users to sensitive data that's onshore. If you really want your data to be yours and yours alone, it is not currently, and it's unlikely to ever be safe. The real question we need to ask is how many bits per second data loss are we prepared to accept? Thank you.
I have a mic in the center of the room if anybody has any questions. If we don't have questions, I have to put that down in his report, and they will revoke his visa.
Again.
We don't talk about that. All right.